Morning, everybody. David Shapiro here with your daily State of the Industry update. As often happens, my newsfeed helpfully handed me this morning. Hydra Attention, efficient attention with many heads. It was a study just released from Georgia Tech and Meta. Okay, so the abstract is pretty straightforward. It says, while transformers have begun to dominate many tasks in vision, applying them to large images is still computationally difficult. A large reason for this is that self-attention scales quadratically with the number of tokens, which in turn scales quadratically with the image size. On larger images, such as 1080p, over 60% of the total computation in the network is spent solely on creating and applying attention matrices. We take a step towards solving this issue by introducing Hydra Attention, an extremely efficient attention operation for vision transformers. Paradoxically, this efficiency comes from taking multi-head attention to its extreme, by using as many attention heads as there are features. Hydra Attention is computationally linear in both tokens, so rather than quadratic, it is linear in both tokens and features with no hidden constants, making it significantly faster than standard self-attention in an off-the-shelf VITB16 by a factor of the token count. Moreover, Hydra retains high accuracy on ImageNet and in some cases actually improves it. Okay, so that's this. So in other words, instead of having 1, 2, probably a square number of attention heads like 1, 2, 4, 8, 16, they just go to have as many attention heads as possible. And what they found was that you get efficiency increases. So I'm going to go ahead and skip down to the results, to 4.4 results. So we present our final accuracy and flop count using Hydra Attention in tab 2, which I believe is right here. Yep. So you see accuracy, they were able to, with just a couple of Hydra layers, they improved accuracy a little bit. But then you look at the, when they added more layers, the total floating operations per second went down 4%, and the speed was increased by 10%. And then this is where I'm not quite sure that I get it, because a little bit further down they say that it's 197 times faster. I think that's because it's in parallel, so maybe each head is faster, but then when you have multiple heads you're working in parallel. I'm not quite sure. I haven't read it. I haven't done a close enough reading yet. But anyways, we present our final accuracy and flop count using Hydra in tab 2 compared to standard OT, et cetera, and other OTD methods. On ImageNet 1K, Hydra Attention achieves 2.4% higher accuracy compared to other OTD methods when replacing all layers. And when replacing fewer layers, Hydra Attention can strictly outperform the baseline standard attention model. With 2 layers, accuracy increases. Okay, so they're just saying what the thing does. Okay, larger images. To explore whether Hydra Attention retains these gains with more tokens, in tab 3, we fine-tune the backwards replacement model from figure 4 at 384 pixel resolution for 30 epochs, using the hyperparameter suggested in 31. This results in a model almost 3 times the number of tokens, which should both accentuate both accentuate the difference between OTD and OT2D attention, and indicate whether the global information propagation strategy of Hydra Attention is effective at these higher token counts. And indeed, in tab 3, we see the same trend with the 224 pixel images. Hydra Attention can increase accuracy by almost 0.6% and throughput by 4.1 with 2 layers, or keep accuracy the same and increase throughput by 15.4. Limitations. Okay, but Hydra Attention is 197 times faster than standard attention. So this is, I'm not quite sure where they got that, other than the only other place it appears here. So I'm not sure if they're saying like global time was that many times faster. Not sure. But if it was 197 times faster, that is a huge order of magnitude improvement. And it's not entirely surprising because we saw that kind of improvement between Google Universal Sentence Encoder version 4 and 5, where it's literally 100 times faster, just with an algorithmic improvement such as this. So if I'm misunderstanding this paper, I'm sure someone will comment. Anyways, but while this number does sound extreme, it's not surprising to me. Okay, so why is the maximum flop count reduction only 4%? Well, it turns out that with VITB 16 with 224 by 224, only 4.1% of the total model flops reside in creating and applying attention matrices. With Hydra Attention, this is reduced down to 0.02%. Wow, okay. Essentially eliminating the cost of attention in the model. While this does result in raw throughput increase of up to 10.2%, we can clearly do better. Of course, the story changes if you increase the image size. We repeat this computation for different size images, and the computation of standard attention balloons all the way up to 58% with 1280 pixel images, while Hydra Attention remains negligible at 0.02. Okay, so basically this makes the first step computationally inexpensive, no matter what size. We test 384 and speed up to Hydra Attention up to 27% increase. However, further work needs to be done to validate Hydra Attention on tasks that use more tokens. Though in those tasks, we'd be comparing against the local window attention used in VITD det. I'm not sure what that is. Which has already shown to be effective for large token regimes in images. Compared to local window attention, Hydra Attention uses only 4% fewer flops. Okay, in general, the usefulness of Hydra Attention lies in its generality. Local window attention is a powerful solution for dense image prediction, but quickly becomes cumbersome with token sparsity, such as with masked pre-training or token pruning. We leave this for future work to explore. Conclusions. In this paper, we introduce Hydra. It can work in tandem. We've taken the first step in showing that Hydra Attention can work at all, and hope future work can explore this in more token-intensive domains. Okay, so what does this mean? One thing that I suspect that this means is when you look at the difference between other transformers, such as Google's Universal Sentence Encoder version 4 and 5, and it suddenly becomes much, much faster and computationally inexpensive, that means that it is ready for universal deployment. Now, it sounds like this is not quite ready for universal deployment, but it is a big step in that direction. Now, imagine if all image-based transformers can suddenly become this much faster and this much more efficient. Imagine if your Dolly and Midjourney and Stable Diffusion generations, instead of taking 15 seconds to 60 seconds, they take half a second or a tenth of a second. And then, so that's just image. But if you look at the on r/machine learning, where one of the authors posted this, someone asked if this could apply to language models, and they said it probably could. So imagine if this allows us to greatly expand the window size of GPT-3 and other language models. What if instead of 2,000 tokens or 4,000 tokens, this allows us to go up in window size by a factor of 10 or 100? Or alternatively, what if it accelerates the inference? Instead of taking 4 to 5 seconds per inference, what if it takes 0.4 seconds or a few milliseconds? And so then if you have a language model that can perform at human ability, but at ultra superhuman speed, then even if it's only human equivalent, but it's many times faster than people, that's still superhuman, because it will do much more work in the same amount of time as a human. Now, they're still energetically less efficient, but the fact that they're faster and they can work tirelessly kind of might bring that down to parity with humans, because when you talk about energetic efficiency, you have to also think about time. Because if something takes you years to do, your brain was using 20 watts over that entire period of time. But if the machine can do it in an hour, even if it uses a lot more energy during that hour, it still might be you might reach energy parity sooner. So taking a big step back, this is when I frequently talk about we'll find more efficiencies, this is the kind of paper that I'm talking about, where because this space is so new and huge and it's growing all the time, we are constantly finding new efficiencies, new algorithmic efficiencies. So one of the things that started this whole thing was an advancement in understanding loss functions. I think that was back in 2014 or 2015. That's what kicked off this entire renaissance of deep learning. was figuring out how to optimize larger and larger networks. And so that one little algorithmic improvement, and then subsequent downstream improvements, enabled everything that we're seeing in artificial intelligence today. And then seemingly small algorithmic improvements like this, which are just small structural differences, right? Like, let's use as many heads as possible. Let's do an experiment. Oh, hey, look, we cut the cost down from 58% to 0.02%. That is a gravimetric shift. That is a seismic shift in the computational cost of some of these things. And as a systems engineer, it doesn't surprise me. It's like if you have a single-threaded application or you have it running on 300 threads, right? If you can divide the work up like that, go for it. So in computation, there are 4 food groups. There's CPU or processing. We also have GPU. So whatever you have a machine that does the processing, that does the math. You have memory. Then you have storage and network. So you have those 4 basic food groups of computation. Now, for a model that runs on a single GPU, you're going to be constrained by that GPU's processor speed and its memory. But depending on how big it is, you might have to be reading and writing to storage. Storage is 1,000 times slower than memory, and network is 1,000 times slower than that, right? So if at all possible, you want to keep all computation bouncing back and forth between your processor and your memory. And with a GPU, you have those things combined into one on a single card, right? Now, if you have to switch to normal CPU and RAM, because GPU has VRAM, right? It's got its own built-in video RAM, so you keep it there. But then if you have to switch to CPU and memory, you have a slower CPU that's not purpose-built for those matrix operations. And then you also have general purpose system RAM, which is usually a little bit slower, right? But then if you're doing really big things and you have to write to disk or swap or whatever, that's going to be much, much slower. And so then you'll end up so in terms of speed, GPU is the fastest by far. CPU and RAM is the next one down. And then if you have to swap to disk, that's even slower. But then if you have to share over networks, granted, you can have specialized network connections to cluster GPUs, but if you don't have that kind of specialized network clustering, going over the network is even slower, because then you're not accessing storage on your local system. You're having to package up everything, communicate out on a network protocol, share data, and all the overhead that networking provides. Now, granted, networking can be very fast, but your fastest backplane might be 10 gigabits a second between one host and another, whereas you might have 1,000 gigabits a second between your local storage if you're using SSDs. So again, right, that's a factor of 100 times slower throughput. Anyways, I'm diving off into other aspects of technology. My point is that it does not surprise me if you parallelize an operation, it goes much faster. But also, depending on where the constraint is, if you have it, so think of it this way. Another way to think of this is, imagine you have one line of cars going down a 16-lane highway. That's what you're doing before if you have just a single head of attention. And so if everyone is constrained to one lane and you have a 16-lane highway worth of traffic going down one lane, it's going to be infinitely slower than if you have all 16 lanes open with 16 lanes of traffic. And so that's why mathematically, when you squish it all, it's not just that it goes 16 times slower. When you have a traffic jam like that, it goes 1,000 times slower, right? Because it's not like the speed limit's 60 miles an hour and you divide that by 16 and you're going 4 miles an hour when you go down to one lane of traffic. No, you go down to a mile every 3 hours, because it's more complex. And I'm not a math expert, but basically traffic jams create bottlenecks that slow the whole system down disproportionately. And that's kind of what we're finding here, is going the opposite way of, oh, hey, we open up more lanes of traffic and suddenly things are going faster than you'd expect. So that's kind of how you see this. And this is something that is true in systems engineering, which is what I do for my day job. So anyways, I'm rambling now. Thanks for watching. This has been your State of the Industry update. Like and subscribe, and consider supporting me on Patreon. Have a good one.